Okay. People are rolling in here. Clement, you're back again. Hi, Eric. I haven't seen your name for a while. Okay. I am going to get us started right here at 10 o'clock. Welcome to today's webinar. It's our only one this February. We have Scott from Snohomish PUD is going to talk about the Arlington Microgrid that they've had there for 5 years, I think, Scott, is that right?
10 years.
No, 10 years. Oh
Well,
my
5
goodness.
years of running, but started 10 years ago. But yeah,
Okay.
you're right. You're
Yes,
more right.
got it. Right. Okay. We're both right. And just let me advance my slide so you know what to expect. If you haven't had a webinar from the Lighting Design Lab before, you are all on mute and off camera, at least for the time being. Hi, Eric Strandberg. Hi, Sadhu. You can submit your questions at any time, though. There's a little question mark icon somewhere on your screen. If it's on your web, it's usually on your right upper side. Go ahead and click in there and type any question you want. And if you just saw Eric Strandberg did a little quick reaction there, you can hit thumbs up, you can hit the heart, you can hit the laugh. That's kind of nice to give the presenter a little bit of feedback because you are all on mute. Um, the webinar is being recorded, so if you have to step away or if you want to ship this out to everybody that you know afterward as a nice little springtime gift, I don't know what I'm saying, you can. We'll have it up on our website within about a week along with the slides. And then the most important thing, after I close everybody out, there's a survey that pops up in your browser window. Please give us some feedback. Any and all feedback relevant to our operations here is appreciated. Okay, and we have 3 events coming up for you. They are not ready to register for. I need to get them up on the website. I'll get that done today. But we have Sean Dara coming back. If you remember him from Lighting Design Lab days past, he's going to come and give us a 2-hour webinar on lighting and implementation techniques. And then we're going to have, we haven't had this for a while, so some envelope training, so fenestrations, envelope, and envelope commissioning. That one is with BEE Engineering, I believe. And then we're going to have cold climate heat pumps there in April. We're going to take the rest of February off because Robert gets to go on a big vacation. And then, as always, the monthly Seattle City Light Trade Ally office hours. If you have questions about incentives or projects that you're doing with our customer energy services team over on the other floor here, that's a time where you get 15 minutes to talk to them one-on-one, shoot ideas for projects by them, get your questions answered. Okay, Scott, are you ready for your presentation?
Absolutely. Yeah, thanks, Katie.
We are ready for you.
Okay, do I need to share?
Yep, you'll need to share that
And
presentation.
okay, so I'm going to hit share. Let's see if we can get this right. Okay,
Perfect.
does that show up? All right,
Yep,
awesome.
and I'm going to be in the background, everyone, or Robert will, off mic, off camera, but I'll be here lurking.
Thanks, Katie. All right. Hey, good morning, everyone. And Katie, I'm not sure if you said this, but so I've got about an hour plus of material, and feel free to chime in with questions in the moment. So you don't have to save all your questions to the end. Katie will be monitoring. You might have already said that, but we'll be monitoring and I can answer questions along the way because it's just a lot of cool stuff, a lot of fun stuff to talk about.
Yep,
So,
just find that questions mark icon up there. You can type them in and we'll get them asked to Scott.
all right. Thanks, Katie. Well, again, good morning, everyone. I'm Scott Gibson. I have been with the PUD about 26 years, and I'm just about ready to retire. So this might be one of my last microgrid presentations. I retire in June, so there might be a couple more. but I love this subject. I love to talk about it. So I'm really looking forward to this discussion, and just ask away with questions, anything you want to know. Um, Again, I've been with the PUD about 26 years. I actually started off in facilities and then over in energy efficiency. And Eric Strandberg, I remember you from the lighting design lab. You have been there a long time. And yeah, yeah, I remember going there, learning about lighting and ballasts and all the latest and greatest, and then helping our customers put those into their offices. So that was a long, long time ago, 20, 25, 26 years ago. So some cool memories. Since then, I worked in energy efficiency and then in distribution, and then got to move into our generation group and help build a couple of hydroelectric projects. Super fun. And then actually got to work on our tidal generation project. We almost moved ahead with that. We were so close to do tidal generation, one of the first ones in the Northwest and one of the first major ones in the country, but it was just too expensive, so we had to cancel it. But really a cool project. And then I got handed the Arlington Microgrid. We had already done a couple of battery projects, but then I was asked to run this one, and I'll get into that a little bit more later. And I'm an electrical engineer, so a double E, so love to talk about all things electrical. So with that, let's get into this. Here's our agenda. I'll just talk a little bit about who the PUD is. Most people know. Talk about where our electricity comes from. What have we done so far? Some of our past projects, and then really focus on the microgrid, and then talk about what is next. So about Snohomish PUD, we're the utility for Snohomish County. We're just north of King County. We cover the territory from Bothell all the way up to Darrington, and then from Index all the way over to Camino Island. So we're the largest PUD in the state. We started up in 1949, population of about 900,000, 367,000 customers. Most of our power comes from BPA, and then we have three elected commissioners that cover different territories. Again, most of our power comes from BPA. We're primarily a distribution company. We buy power from BPA and then we distribute it. We do have a few small projects. Jackson Hydroelectric, it's about 30 years old. Youngs Creek, Hancock, and Callaghan, those are three run-of-the-river projects that started. They're about 5 years old now, and then another run-of-the-river hydro project, Woods Creek. So that's about 10% of our power. So that's who we are. So things have changed for us a lot in the last year. So prior to last year, kind of the end of last year, we were still primarily a BPA customer, but we were called we had a contract with BPA, what was called block slice. We got a block of power and then a slice of anything that was extra. If it was a really high water year, we got a slice of that power. And so 66% of our power came from BPA, and we generated about another 7% or so. And the rest of it, we had to go to the market for. And that bit us, and that's why we changed. So over the course of 2 years, 3 times we had really high market prices. There were 2 cold snaps and 1 really hot summer. And during those 2 cold snaps and that hot summer, we had to go to the market and buy power, and spent each time about 40 million that we didn't have. Yeah, 110, 120 million dollars that we didn't have. So we wanted to reduce our exposure to the market. So we changed October of 2025 to something that's called load following. So now BPA really provides everything for us except what we generate with our own projects. So BPA is now 94%. we have no market exposure, we have no wind contracts, and then we still have our 6 to 7% of our own hydro. So now we are almost completely reliant on VPA, and no exposure to the markets. So that's where we are now. And hopefully things stay very stable with BPA. We do know that loads are growing. Water, unfortunately, is shrinking in the rivers. And so we don't know what that's going to do to BPA in the future, but we've locked into a contract that will hopefully hold things stable for our customers. So that's where we are with our electricity needs. So what have we done in the past? There were a couple of projects that led up to the microgrid. One was Mesa 1 and then Mesa 2, back to Mesa 1 here. So we called them MESA. It's an acronym for Modular Energy Storage Architecture. It's a standard for battery storage. It actually just became an IEEE standard, 1815.2. It's a DNP battery storage DER standard. Puget Sound Energy, and I think Seattle City Light was part of it at the start too. They've dropped out, but hopefully they will rejoin and be part of this alliance around this standard. But I can talk more about that standard later on if anybody has any questions. But we helped get that standard going, and hence that's how we named our projects Mesa 1, because they followed that standard. And this was one of the first lithium-ion projects in the country. Definitely the first one for us. About 10 years ago, it was completed. 2016. Last year, we decommissioned it. We learned a lot from it, but it was Gen 1. It was one of the first generation battery storage projects, and we weren't getting a lot of use out of it, and it was just getting hard to maintain. So we decided to learn again from it and decommission it and recycle it. So we worked with a company called Redwood out of Nevada, I think near Reno, Nevada. I think they set up right next to the Tesla factory, and we worked with them to recycle the batteries. We can talk more about that in detail if anybody has any questions. But that project is fully decommissioned. Mesa 2, this was one of the first flow battery systems in the country, and both of these projects we got Clean Energy Fund 2 grants. That's the State Department of Commerce grants for projects like this. So they helped fund it and helped us learn. So we're not doing this completely on our own. So Mesa 2 was a flow battery. A flow battery is where you have a liquid anode and a liquid cathode. So theoretically, on paper, they have a really long life. You can see all those containers. The power of all of those containers isn't that much different than these two lithium-ion boxes. But for a flow battery, we needed a lot of electrolyte. It was about 90,000 gallons of hydrochloric acid, which is a great electrolyte, but it causes so many other problems. We could not stop the leaks. This thing was leaking. It would overcharge and burp electrolyte out onto the ground. And so eventually we just had to shut it down. Flow batteries have a future. It's just not quite now. Hopefully they get figured out in the future though. But we had to shut this one down. We decommissioned it in 2022. There wasn't a way to recycle the material, unfortunately, so we just had to dispose of it. And that was quite expensive. That was a couple $1,000,000 to decommission this one. Whereas the lithium-ion batteries, I think we spent $38,000 recycling them, and those materials will get used, especially the cobalt and the nickel. That's all valuable material. So those were the first two projects. We learned a lot from those. They were studied by the University of Washington. They were studied by the labs, PNNL, Pacific Northwest National Labs. A lot of reports were written about them. We had to because of the grant, and then we learned a lot by decommissioning them too. So the next project is what we're going to focus on, is the microgrid. So the Arlington Microgrid was started as our third battery storage project. And I apologize, I got kind of at the tail end of a cold here, so I'm going to be drinking some tea and trying to keep my voice going. But this project was started with the point of taking advantage of another Clean Energy Fund grant. They were doing another round of grants. So we took advantage of a $3.5 million grant from Department of Commerce, and we designed this project to do everything that you could possibly think of with battery storage. We sat around in a room. There were probably maybe 20 plus engineers and planners and system protection people, and we just brainstormed what could we do with battery storage. And we filled a whiteboard full of all the different things we could do with battery storage, and we did all of them, which created probably the most complicated microgrid in the country. Hitachi was our vendor, and they said at the time it was the most complicated project they've ever done. Just recently, we've greatly simplified the project just to make it more reliable, but we got to experiment with a lot of different things. We got to prove that you could use it for renewable energy integration. We got to prove that you could use it for grid support, ancillary services, peak shaving, volt var, frequency support, voltage support, all that kind of stuff. We could use it for resiliency instead of a diesel generator. And we also experimented with electric vehicles, V2G, bidirectional charging, because really an electric vehicle is just a battery on wheels. So we wanted to prove that if you had enough of these vehicles in a fleet, you could use them to supplement your big battery. So you could see this is a really diagrammatic, not electrically correct for all your engineers out there, but very diagrammatic diagram of the microgrid. All of our generation sources are across the bottom. The electric vehicle, we had 2 Nissan Leafs. We had our solar array, 500 kW. We had a battery, Samsung batteries, an ABB Hitachi system, and then we had a diesel generator as a just in case. That's where all of our power came from. And then a microgrid is really designed that if the grid goes away, you use those sources to keep critical loads going. And our critical loads were a building, our clean energy center, a backup data center for us, and then we just recently built a local office. So this microgrid currently is the backup power source for all of those different things if the grid goes away. Normally we're connected to the grid, as you can see, but if the grid goes away, we seamlessly disconnect, not a blink of the lights, which has been really, really hard to do. You need a grid forming inverter to do that. But if the grid goes away, we disconnect and we keep all those other loads going. And we do need load shedding, so because obviously we can't supply everything, but we shed the non-critical and keep the critical stuff going. So that's a diagram of a microgrid. So for the Clean Energy Fund 2 grant, we proposed that we would do all those things. And I've already talked about this, but we'll skip over that. But those are all the things that we proposed to do, and we got our grant. We started work. The project all got started. Really, the idea of the project got going in 2015, 2016. We got our grant awarded 2017. Then we hired the University of Washington to do all of our reporting because that's a grant requirement. We hired Burns and McDonnell to do all of our design work and help us put together the spec and the RFP to go out and bid for equipment. And then we started all of the construction while we were working on all of that other stuff. We started the site work in 2018. We built the solar project first, so that we could turn it into a community solar project. More about that later. Then we awarded our equipment and controls. We built our clean energy center and the data center. Then we started a civil construction and the microgrid construction, which we ended up doing with our crews. Because it was 2020, that was a super hard time to get contract crews. So we chose to use our crews to actually build the thing. And then we commissioned and had it all done in 2021. Really a tough time to be building a project. This is what it looked like when we started, just before construction in 2018. We had bought 26 acres up in Arlington, right next to the airport. I think it was an old strawberry field. And then we started to fill it in, and now it is just completely full of our office and solar, and I'll show you a cool picture of what it looks like in a little bit. But the yellow is where our solar went, and the two little red boxes are the microgrid and the clean energy center. So a lot of changes in the last less than 10 years up there. Here is what the solar looked like. We rushed that through to turn it into a community solar project. Had it finished in 2019. There was a Washington production incentive that I think we had to be done by May 1st for that, to be able to get that incentive so that we could pass that along to our customers. So we awarded that contract. We had it all done in about a year. We awarded the contract to A&R Solar. They worked with us to spec all the equipment. Then once it was ready to go, they came in, and within 6 weeks, they had this finished. And let's see, Katie, are you there? Or Robert?
Yeah, I'm here.
Okay, let's see if we can play this video. This is the construction of the solar. It's pretty cool. Let's see if we can make this work. We got it to work earlier. Let's see what happens here. Boy, it is tricky. Let's see. Okay, here we go. Let's see. Do you see it, Robert?
No, what you had to do last time was drag that window into the window that's displaying when you got the Vimeo going.
Did that work?
Not yet. Not that I'm seeing.
Okay, how about there? Let's see. Stop sharing. And then give me a second here, everyone. We'll get this going here. It is kind of cool if we can make this work.
I think we're getting somewhere. No.
Did that work?
Not seeing it. Yeah, last time when you got the video playing, you drug it into this window and it worked last time.
Yeah, let's try. Okay. Bear with me. Let's try this again. Yeah, so many screens. It's kind of.
Do you want to continue? Oh, I see it.
You got it? Okay.
Yeah.
That worked? Okay. Boy. Sorry, everyone. Okay, so the community solar, this is just kind of a fun video because you can see how efficient they are with solar now. This was done complete. They started and were completely finished in 6 weeks. So here you go, just a quick little video.
And it doesn't have sound, correct? We don't need to hear it.
Yeah, yeah,
Okay.
no, no. Okay,
All right.
and
Let me
close
put in a
that down.
couple. We got a couple of questions that have come by, Scott. So let me put those
Yeah,
in here now.
excellent. Okay,
And
let's go back
yeah,
to
sure. Get back to the presentation.
um, see if I can. Give me a second here. Okay, are you back?
Yep.
Yep.
Yeah, we're there. Okay. So
Okay,
couple
go
questions,
ahead.
please. The Mesa 1 that was decommissioned, what were the maintenance issues that caused that one to go away?
Yeah, good question. This was a bit of an experiment with two different companies. One was LG Chem and the other one was Mitsubishi GS Yuasa. And we were, uh, the battery management systems were first generation. We were constantly having issues with them. We didn't have any fire issues, no, nothing like that. But it was just communications, battery management, just constantly getting little errors that always had our crews responding and checking things out. And we were ordering spare parts. It was getting more and more difficult to get all of the spare parts. We could do it and we were limping it along, but we were spending a couple $100,000 a year to maintain a project that at the time we were getting very little value out of it.
Sure.
And it was just really taking up a lot of our substation crews' time. So we just
Yeah.
chose to let's let it go, focus
Yeah.
on the new generation stuff, and move ahead.
Okay. Didn't make sense to me. Okay. Regarding the microgrid, couple things there. You said it was the most complex one ever done. And so maybe what was complex about it that other people weren't doing? And then you
Yeah,
talked about simplifying it. So what has been simplified?
yeah, good question. So we we did, oh man, so many things. First of all, we experimented with electric vehicles. We had a control system that would in our electric vehicle, our bidirectional charger was one of the first ever built for Nissan. It was from Japan, a company called Mitsubishi. And so the controller had to communicate with this Japanese system that wasn't approved for use quite yet with the vehicle. So it was just a lot of software to allow for the communications with the electric vehicles. Um, the other thing was we had to do load shedding with different buildings. We had to monitor the battery, and if the buildings if the battery was starting to go dead, we would load shed non-critical loads in the buildings, which we're still doing that. That's still a good one, still an important one. The other one was we were doing solar smoothing. We were using the battery to firm the solar. When there was fluctuations in the solar, we would use the battery to step in and smooth out. Like if a cloud comes over and blocks the sun from the solar, we would discharge the battery to fill in that gap. And when all of a sudden there was a lot of sun and we had a spike in solar output, we would charge the battery to smooth that out. And so it was just a lot of, and then just integrating the diesel generator. We would use the generator to charge up the battery when the sun wasn't there. And there's a number of other things too. We integrated a DERMS system. It was a first of its generation DERMS, distributed energy resource management system, to do peak shaving when the value was there on the grid. So just all of these little things caused the microgrid controller to really have to do a lot of thinking. And then we also had a first generation grid forming inverter too. So, and we were trying to make it switch from grid following to grid forming. All of those things caused little problems here and there. And we've been struggling with it up until kind of towards the end of last year. Last year, we decided that let's just have this thing function as a backup power source. Let's have it just function as a microgrid and not try to do grid support and electric vehicle stuff. Let's just have it do its basic function. And we've been having it, it's been functioning very reliably since then. So a lot of words, just, yeah.
Okay.
Thank
you.
Yeah.
Continue wherever you were.
Okay, thanks, Robert. Good questions, though. Yeah, tough to answer quickly. But so solar. So we, as I said, we turned it into a community solar project. It was our first one. It was the biggest community solar project in the state at the time. I think it still is. Not 100% sure on that, but it's sold out. We sold shares to our customers. We split each panel into fifths. So we sold about 8,100 shares. You can see all the numbers here. It was a great, because of the Washington production incentive, the Washington state incentive, our customers, for every kilowatt hour, they'd get credit on their bill for 6 cents, and they would get a check from the state for 16 cents, so 22 cents per kilowatt hour. And so they, I think they expected, it was a 20-year contract, and their return on that was $186. So I think their expected return was about 6 or 7 years that they would get a payback on they'd get a payback in 6 or 7 years for a 20-year project because of that Washington production incentive. So it was that Washington state incentive. So it was really a good project. That's gone away. We're still going to do more community solar. It just won't be as lucrative in the future. But this was a good one. Here, now I'm just gonna show you some pictures of the start of this microgrid because it's kind of fun. You can see the solar was done by 2020. We had started building the wood framing there is the start of the Clean Energy Center, and that big concrete pad was the start of our data center. So this all got going, and then on March 23rd, everything came to a halt due to COVID. Everything shut down, as everybody remembers in the past, a long, long time ago. So we shut down. We wanted to keep the project going. I wanted to keep the project going because I had equipment on order. I had equipment coming in. I had to try to figure out what to do with that equipment that was going to start arriving very soon. That was a challenge. So we got approval from our commission and the state that we could actually restart this and keep us safe with social distancing. So we restarted June 1st, 2020. Everybody's wearing masks. Everybody's keeping their distance. It was an outdoor project, so by its very nature, it was easy to keep our distance and keep the project going. So the civil contractor got going, putting in pads and conduit, and started digging up that whole area where you see everybody standing. And that's where the microgrid was going to be constructed. So that whole area turned into a massive amount of conduit and concrete pads in the next couple of months. So, and this is what it looks like now. So where everybody was standing, you can see on the right, that's where all the equipment is. Our battery, our diesel generator, the 40-volt switch gear, our 12 kV transformer, and where we step up to 12 kV and then go out onto the distribution system, the solar over on the right, our Clean Energy Center up on the left, and then our two electric vehicles, our two Nissan Leafs next to the bi-directional chargers. And then up to the upper left is where our data center was put in. It's not, doesn't look like much, but that is our entire backup data center. Our main data center is at our operations center, and if something happens, an earthquake, whatever, that takes out that data center, theoretically we can seamlessly transfer over and use this data center, and the microgrid will help keep it powered up. One of the cool things about that data center underneath it, when it was going in, a big auger, big giant auger came in and drilled 100 holes 70 feet deep, about 18 inches in diameter. And when the auger was pulled up, they filled all of those holes full of rock. So there's 100 holes 70 feet deep, 18 inches in diameter, just full of a massive amount of rock underneath that data center to hold it steady in case there's an earthquake. And then all the conduit and all the connections are on flexible conduit, so it should stay standing. So that's what our microgrid looks like now. Sorry, I tried to keep my voice going. Here's just another picture of it. We did, and you'll see a rendering, but the solar that's on your right, the last 4 rows there, we relocated over to the left because that whole area is going to be filled with our biggest battery system yet, probably the biggest in the state. It'll be a 25 megawatt, 100 megawatt hour battery energy storage system, Tesla batteries. And I'll show you a rendering of that later on. But just another picture of our microgrid. So here's just some pictures of when everything was going in. Here's when the battery was being set. 14,000-pound container, and then they loaded another 14,000 pounds of batteries, about 120 modules. They were 70 pounds a piece, so they used a telehandler instead of trying to pick them up individually. And one of the things, so we built this project in 2020, and it was impossible to do factory acceptance testing and factory visits and make sure that everything was good before it arrived. So we really had to try to do teams and go-to meeting factory acceptance tests, and it sort of worked, but almost every piece of equipment that showed up in 2020 was lost or damaged or missing something. So our crews were constantly repairing things. And these batteries, and that happened quite a few times. And we knew the batteries were coming in, and we told ABB, it was ABB at the time, now they're Hitachi bought them out. But we called up and we said, hey, this has happened too many times. Please make sure those batteries that are coming in from the East Coast, coming in from Samsung, hitting the East Coast and then getting trucked across over to the West Coast, please put those on a dedicated shipment, one driver, make sure they get here. They are lithium-ion batteries. It's hazardous material. Please make sure they get here. Well, we're all ready. We all get out there early one morning. The batteries are supposed to arrive 8 a.m., 9 a.m., 10 a.m. They're still not here. They didn't arrive. So I called up our contact at ABB, said the batteries haven't arrived yet. And they said, well, what the heck? It was on a dedicated truck. They should have been there by now. So they started calling around. They found out that for some strange reason, the driver had dropped them off down by SeaTac at a warehouse. So after some searching, they found out that all of these lithium-ion batteries were just piled up in boxes in the middle of a warehouse. Nobody had any idea what they were. For some strange reason, the driver decided it was a good idea to drop them off down there and then just go home, even though he was supposed to be a dedicated driver. So they got another truck, they picked him up, they brought him up, and got him delivered to the site. And then we started seeing these forklift holes poked into the boxes. Like, what the heck? So whoever was loading these things up didn't know what they were, didn't really care about them. Fortunately, only one of the modules was damaged. And lithium-ion at the time, we were super worried. Everybody was incredibly paranoid about handling this lithium-ion module. It ended up being just fine, but it was damaged. We had to get a new one from Samsung and get that one replaced. But it did give us an opportunity to rip one of them apart and see what was inside, which was pretty cool. And then find out how much it cost to recycle them, which it cost at the time. You couldn't recycle them 5 or 6 years ago. You just had to dispose of them. And it cost as much to dispose of them then as it did to buy a brand new one. So we got everything up, got everything loaded up. You can see everybody's still wearing masks. All the modules are in. We're ready to start powering this system up. So this was a custom container. When we spec'd this thing, at the time, we wanted it. What we thought was we wanted it to be easily maintainable. We wanted all the batteries on one side. Unfortunately, what that meant is that you had to stack the batteries really high. So we've learned a lot. No other battery systems will be designed like this. Now they're just in connexes, and they're really all commodities. But at the time that we spec'd this, fire safety systems were kind of a pain in the butt. And I didn't want any of them because it just seemed like they would always fail. And at the time, all the vendors were saying that battery fires aren't a problem. That was 5 or 6 years ago. Don't worry about fires. Everything's safe now. Just don't worry about it. Well, we went out as we were out to bid. The fire down in Peoria, Arizona, Peoria, Nevada. Now, correct, you have to check me on that one. Happened, and a battery exploded. It threw a bunch of firefighters underneath a substation fence. Didn't kill anybody, but it was really a bad event. And it was because explosive gases built up inside of a battery container after it had caught on fire, because there wasn't a way to vent the explosive gases. After that happened, we completely changed our spec, and we said, okay, now vendor, we want you to do everything known to humanity to make these batteries safe. So we had them put in everything you could possibly think of: smoke detectors, Novak 1230. It's what you use in a data center to put out fires. We put in water. We put in lion tamer, which is a way to detect thermal runaway early on. So we put in all of these systems, and we worked with Pacific Northwest National Labs to design a system that if there was a fire, it would automatically open the doors so that it would vent any gases, and that nobody would ever have to be the first one to walk up and open a container. So we did all of that stuff kind of mid RFP for the batteries, and the vendors did it, but not without a lot of complaining. And since then, a lot of these systems have been written into all the new fire specs, NFPA 855. So now they're required on almost every system, but we had to learn it the hard way and learn about it, why it's all so necessary. So these are all the different things that we put in. I'm not going to go through it all, but you can, yeah, we put in everything you could possibly think of to make that a safe battery. And so far, we haven't had any issues with it. One of the things that we learned that was incredible, and we'll talk about this in lessons learned, we brought in the local fire department right away, and they helped us design this system. They got comfortable with it. They had to approve all the permits for it, the fire alarm permit, all the sprinkler permits, all that kind of stuff. So they were brought in to help design the system, and so it was much easier for them to sign the permits. And every year now, we use this system for training. We bring them in, we do on-site training, and it helped get them more comfortable with the 25 megawatt Tesla system that is going in right next to this. So incredibly important to bring the fire departments in right from the start. This is just a picture of our electric vehicle system. We had just the bi-directional chargers. They were made in Japan, Mitsubishi, and all the writing came in Japanese. So we had little translator labels underneath all the Japanese labels, which was kind of fun. And then all of our meetings, which was another fun thing. The meetings were in the evening for us, and then the morning for Japan. And we'd call them up. We'd get started with the commissioning, and then every morning they'd have to break for prayers. And so we'd take a little break for prayers, and then we'd get back to work. And really a fun time. And we could really see why things that come out of Japan they're meticulous. They're made with the highest level of detail. They were perfectionists, almost aggravatingly so, but we got the system to work. It was pretty cool. These are all the things that just some more, and just another picture to show you what we did with the microgrid. When we were grid connected, we'd use it for grid support, renewable energy integration, energy arbitrage, demand reduction, peak shaving, electric vehicle integration, solar smoothing. So we were doing a lot when it was grid connected. When it was islanded, then that grid forming inverter would take over, and the grid forming inverter would be the balancing authority. It would maintain the voltage and the frequency. When we're grid connected, it just follows the grid. BPA, the Bonneville Power Association, is our balancing authority, our BA. They maintain voltage and frequency, and we just followed it. When we're islanded, that grid forming inverter had to take over and do all that. That's the beauty of a grid forming inverter in electronics. It had this power conversion system. The battery inverter had software in it called virtual generator mode that would allow us to do that. So pretty cool stuff. Lessons learned, and then I'll talk about kind of what the future is, and then I know we're kind of getting towards the top of the hour, and then we'll save time for more questions. Lessons learned, collaboration, and we are still learning this to date. Microgrids are still complicated. They are not just off the shelf, out of the box things yet. It still requires a lot of collaboration with whatever vendor you're using. So that's incredibly important. You got to pick a vendor that has a solid track record and that you're going to be able to work with, and one you can trust. So super important there. Battery energy storage safety. As I said earlier, engage with your first responders, your fire departments. Get them comfortable, because unfortunately there still are battery fires. Every couple times a year we'll hear about a system catching on fire. So what we've learned is that you don't try to put out the fire, you just let it safely consume itself. You just keep it from exploding. You need to vent the explosive. You need to vent the hazardous gases. But then you just kind of stand by, protect everything around it, and let it safely consume itself, because you can't put out a battery fire. You can take a battery module, most of you already know this. You can take a battery module, put it into thermal runaway, drive a nail through it, whatever, and then throw it in the ocean. And that thermal runaway, the fire might be extinguished, but the thermal runaway will keep going. And if you pulled it out of the water, it'll just burst right back into flames. So it has to run out of all of its fuel before that thermal runaway stops. Putting water on it doesn't stop it. So safety is incredibly important. And then microgrid modeling. So I think we're still figuring out the best way to model these things and make sure that they can interact with the grid and not cause problems with the grid. So we're still, I think all utilities are still struggling with that a little bit. And grid forming inverters are still relatively new. Vendors are still having some issues with grid forming too, just making sure that they're stable on the grid. So got to make sure you pick a good vendor and is willing to stick with you while you iron out the issues there. And then standards. It's important to follow standards when you're doing these things. And MESA, which just last week was officially adopted as an IEEE standard, IEEE 1815.2. If anybody wants to know more about that, I'd love to talk about it, but it is officially an IEEE standard for battery systems and DER. So pretty cool. Those are really important lessons learned. Collaborations. Here's just all the collaborations that we had and learning opportunities that we had with our project, which we continue to learn, but we were a big participant with MESA. We worked with UW on modeling and simulations and looking at all the data. We worked with the labs, government labs, Department of Energy labs, to to analyze things, analyze the data, and write reports. We work with the University of Texas on grid forming inverters, Mitsubishi on understanding V2G. We still have a pilot project with BPA to understand how to better use batteries and what the value is for solar smoothing, solar firming. We worked with the Washington Clean Energy Test Beds on solar panel testing, and then we've just engaged with a lot of other utilities to compare notes. So a lot of learning with this project. Additional benefits, we've learned a lot about how to design these things, what the costs are, permitting. Permitting is still a challenge. In fact, it might be our greatest challenge, getting these interconnection agreements and permits done so that we can move ahead with design and construction. But we've learned how to navigate that process a little bit better. Not perfectly, but a little bit better. We're still working on system protection and interconnection issues. And with all of this stuff, our customers now are coming to us wanting to know how we can support them on their microgrids. One of the guys in our department is working with the Tulalip tribes to build 3 or 4 microgrids, and then we're going to connect them up with our own 12 kV system. So that is just getting started. Maybe next year, Alex Corey, who's working on that, can do a presentation for you and talk about that project. But super cool collaboration with the Tulalip tribes, and then just continuing to work with other utilities too. And then our Clean Energy Center, we do a tour, if not 2, a month, and from people all over the world. We've had Thailand, we've had the Netherlands, we've had Spain, utilities from all over the country, universities, K through 12 schools. We do a lot of tours here. Really a fun place to learn about microgrids. So really it's turned into a cool facility. And the future of energy storage in the Northwest. Things have not stopped. Energy storage is becoming even more important with peaks getting higher. Winter, except for this winter, this hasn't been much of a winter, but in the past, our winter peaks have been pretty high, and our summer peaks are getting higher. It used to be that we had like single-digit percentage, maybe like 5 or 6% of our customers had air conditioning. Now I think we're at about 40%. So our summer peaks are getting higher. So energy storage is really uniquely positioned to help as a grid resource, a capacity resource. We are getting capacity constrained here in the Northwest. We're at a risk of not having enough resource adequacy, enough capacity, and battery storage can step in and help there. And so that is really the genesis for our next project, which, I'm gonna skip over this because I think everybody understands what's driving the future, our policies, I-937 and CETA. So I'm going to skip over that. What it means is all of this just means that we need more battery storage so that we can reduce those peaks, because those peaks, we used to have gas peaker plants that we could fire up and help shave those peaks, but you can't do that in Washington State anymore. So at least, by 20, I think I don't think there's any more gas being built in Washington State. And by 2040, 2045, all gas has to be gone. Nobody's building more gas in Washington State, at least that I know of at this point. So batteries are one of the ways that you can use to shave those peaks. And that's what we're doing. So we signed an energy storage agreement with Ameresco. This is just a rendering of the project. This, you can see where the Clean Energy Center is. You can see the microgrid and where the solar is. We moved part of that solar over to the left to make room for a 25 megawatt, 100 megawatt hour battery system. It's going to be Tesla batteries, Tesla megapacks. I don't think that shows it all correctly, but there's going to be about 27 or 28 containers there. 100 megawatt hours worth of batteries. It's a 25-year agreement with Amoresco. We pay them a monthly charge to be able to use those batteries, and they are responsible for all the construction and the operations and maintenance. We're the dispatcher, but they have to do all the other operation and maintenance on it and keep it going for 25 years. So that should be online by the end of this year. We're one of those permit things. We're building a new substation. The new substation is going in over on the right in that box, and we have to build a new transmission line. We've had a heck of a time getting that transmission line permitted, and I think either by the end of this week or by the end of next week, we'll actually get our final permits and we'll get to move ahead with it. The substation is almost complete. The transmission will be completed this year. The batteries should be showing up probably in a month, and everything should be converging on getting this done by November of 2026. So pretty cool. The challenges with all of this stuff are permitting, siting, safety, life cycle. So the engineering is pretty straightforward. Not perfectly streamlined, but pretty straightforward compared to all of these things. You got to find the land for this stuff. Land is expensive. You got to make sure it complies with all the zoning codes. You got to make sure that the cities are going to allow for that use. Are they going to be okay with having batteries in their area? So you got to really start early with all of these discussions. We're going to build a 1 megawatt solar array up near Stanwood, and we're going to hopefully take advantage of the IRA tax credits. Those all have to be safe harbored by July 3rd, July 4th. And so we're really rushing through trying to make sure that we can use that property for solar, that the city of Stanwood's going to be okay with it, and just trying to get because the engineering is pretty straightforward. The engineering on the solar array is incredibly simple, but making sure that we can get it permitted and get that tax credit, those are the challenging parts. And then battery challenges, just got to make sure almost all batteries are LFP now, lithium iron phosphate. We've moved away from cobalt, at least for utility scale stuff. Cobalt comes from the DRC, Democratic Republic of Congo, and a lot of unethical labor is being used to get that material. So almost everybody is speccing lithium iron phosphate now. It's also it's less energy dense and less prone to fires too. So all of these different things. And then you got to make sure you have a plan for end of life recycling. And so we've learned a lot about how to do that. So just here's more about sourcing. And here's a great diagram of all the different codes that you need to follow when you're putting in a battery energy storage system. There's a lot. I don't see Mesa on there, 1815.2, but we'll have to update this slide to show that now too. Recycling, talked about that. If anybody has any questions, we can talk more about how that was done, the costs there too. And, I think that is an hour of me talking, I would love to now open it up and spend the next 20 or 30 minutes just open discussion and just answering questions. Um, Katie, Robert, does that sound good with you?
I'm making Robert do it.
That's
Okay.
fine. I usually manage to hide during these, but this fine. So we'll just start. Um, what about iron flow batteries? There's a company in Portland that does it. There's a uh, so any experience, or have you looked at those? Yes, no. What caused you not to choose them?
Yeah, absolutely. Iron flow. So there's vanadium flow batteries. That is what we experimented with. Iron flow is another type of flow battery where you don't have to use vanadium. Vanadium's kind of a more expensive material, and most of it comes from China and processed in China. But again, it's still a flow battery, and that technology is still not quite ready for prime time. The labs, especially PNNL, Pacific Northwest National Labs, just built a giant facility over in Richland to test new battery technologies, and flow batteries is one of their focus, and iron flow is one of them. So they're testing them, trying to get them ready, but they're just not quite. They're not as ready and as economical as lithium ion. Lithium ion is going to be dominant for quite a while. So it's on our radar though.
Okay, that kind of leads into the next question. What are your predictions for the futures of battery technology? I mean, what chemistry, what form factor, solid state, flow, what's coming, what looks promising?
Yeah, boy, I wish I had a better. I think the simple answer for now is it's going to be lithium ion for maybe the next 3 to 4, maybe even 5 years. There is technology called silicone ion and sodium ion. And I think it's a company called Group 14. They were building a factory over in Eastern Washington, and they were looking at silicone ion. So getting rid of the lithium. So I think I think for now there's still just going to be improvements to lithium, moving more to that solid state form that we had talked about to make it more reliable, more stable, more cost effective. So there's just going to be improvements in lithium, but maybe in 3 or 4, 5 years, silicone ion and sodium ion will start to displace some of the lithium. And then when we say solid state batteries, that doesn't mean electronic batteries. That just means that that the electrolyte isn't a gel, it's more of a brick, more of a solid. So it's just more stable. But that's my prediction for now. I think flow batteries are sometime in the future, maybe in 5 years, those things will become cost effective. There's certainly a lot of people working on that technology. There's iron air form. There's a company called Form Energy.
Right.
So one of the founders of Tesla, and that's just using rust.
Mm-hmm.
That's the first battery was invented more than 200 years ago, and that was just rust back then. Form
Yeah.
energy is just another,
Yeah.
but it takes a massive amount of land because you have to have a lot of iron, a lot of space, and you're just
Yeah.
relying on rust to generate
Just
electricity.
yeah. For the audience edification, we did a webinar a year ago or so that had both Form, which is this iron rust battery, and ESS, which is the iron flow battery. So we had both of them present on a webinar a little over a year ago. So you can go find that and get more education about those two things. Next question here. In the one module, you'd stack the batteries way too high for practical maintenance access and whatever else. What have you learned? What's the answer now?
Yeah, good. Yeah, we thought we were being really smart. We thought, okay, let's have everything on one side so the fire department can see it. They can see everything that's going on. It's easier for maintenance. You just have to open up these doors to get to it. But then we realized that like those whole top 3 rows are just super hard to get to. You got to do it from a ladder, and those modules weigh 70 pounds a piece. So um, nobody is doing that anymore. Everybody is using a Connex type form factor for the battery container, and it's about as tall as if you took off those top 3 rows, it's about that tall now. So this was a custom container, excuse me, made for us, and we thought it made a lot of sense, but once we started using it, we realized that it's just too tall. And then it also allowed for all the HVAC and cooling, ducting, and sprinklers to run inside there too. So there's a little bit of a benefit to having a taller container, but almost all vendors are it's quite a bit shorter, probably about 5 or 6 feet shorter now. Again, just like a Connex.
Okay, can you talk about the load shedding strategy that you're using? What loads are you shedding? What are you trying to maintain? That sort of thing.
Yeah, good question. So we basically we start by shedding HVAC loads, so the big heavy loads. Um, in the event if the battery's starting to run low, we'll shed those loads, and then we start to move to lighting that's not essential. And then what we want to do is keep any anything going that allows people to work, computer loads, office lighting, things like that. We just make sure little data closets, we keep those things going. But if it's the middle of the night and the battery's starting to go dead, it'll be first HVAC. Things might start to get a little bit colder or warmer, depending on the time of year. And then we shed non-essential lighting. And then, yeah, what else? Probably really
So,
just kind of things
so
like
how
that.
many hours do you expect to run on the battery, and at what point do you start shedding things?
Yeah, when the battery gets, we have a load shedding scheme, a pretty complicated one. When the battery gets to about 50%, we start load shedding, and we have about 4 or 5 load shedding levels where we'll shed this equipment, and then we'll shed this equipment. And if the battery continues to draw down really quickly and we get down to about 20%, we don't shed any more load. We then instead start up the diesel generator. And then the diesel generator runs until we get the battery charged back up again. And we kind of go back up the ladder of bringing load, restoring load. Yeah, so it's as the battery starts to get drawn down, we'll shed load, we'll shed load, we'll shed load, we'll shed load until we get to a level where now it's critical stuff that people need to keep doing their work. And then we fire up the diesel generator and let the diesel generator start to charge things back up again. We just want to preserve that diesel, because if there's a big earthquake and one of the big massive earthquakes, and we're down for who knows a couple of months, and roads and bridges are damaged, we only have 1,000-gallon tank. We've got to try to preserve that diesel fuel as much as possible. So we load shed, and then use the generator only as necessary to preserve that fuel. So a lot of things having to be thought of while we're going through that process.
Okay, so you had gotten rid of the one system because basically the maintenance cost was too high. So what are your
Yep.
present O&M challenges for the battery energy storage and the PCS?
Well, it's yeah. What's a good slide to get back to? Um, so I think the current challenges we're just getting that grid forming inverter to not trip. Um, so we've completely gotten rid of the electric vehicle, the V2G, just because it was a great experiment, but not really practical. We've stopped doing the solar smoothing with the battery because that just was requiring the battery and the inverter to do too many things all at once. And now we're just really focused on making that inverter, that grid forming inverter, be as reliable as possible. And that is what's caused us the most issues probably over the last 6 months, is transitioning from grid following to grid forming. And the vendor recently has figured out a way to just always keep it in grid forming mode. So we've switched to grid forming mode 100% of the time, and now the system seems to be very stable. So now, knock on wood, theoretically, our maintenance is going to go way down while we just focus on making the system function as a backup power source. And our main focus is reliability. Once we get that all perfectly nailed down and we're really comfortable with reliability, then we might start to add in other things. The solar, the inverter, the solar inverters, they're no problems at all. Very, very, very low maintenance, very reliable. Once a year, we clean the panels. We go out and we just hose them down, simple green cleaner. We hose them down and clean them, clean all the mold and dust and bird poop off of them. Other than that, that's about it. So hopefully that answers that question.
Sure. Okay, you've mentioned getting rid of the vehicle to grid. Can you talk more about the why in regarding that?
Yeah. So the intent, we got rid of the Mitsubishi Chargers. We stopped using them just because it really, they aren't practical. Each of those chargers were $50,000. We were constantly losing little blips in communications because we could make it work, but we couldn't make it work all the time. So we were troubleshooting the little communications boxes and little things going on. The communications with the vehicle wasn't perfect, so it would work, but it wouldn't work flawlessly all the time. So we were spending a lot of time just tweaking it. And we decided that, hey, this isn't a system that anybody else will ever use. Let's just let it go away. Let's quit supporting it. We proved we could do it. It's just costing us a lot of money to keep it going.
Sure.
So what we talked about doing is replacing those chargers. There is a new one that Nissan is going to use, has approved for use with their vehicle, and Ford, the F-150 Lightning, has approved one for use with their vehicle. Mm-hmm. So possibly next year or the following year, once we've gotten a few other things done, we might go back in and replace both of those chargers with one that's approved for use with a Nissan and one for use that's approved with an F-150 Lightning. So something that is more practical and our customers would actually be able to buy. So we're not done with it, We just want to move on to newer generation
Yeah,
stuff.
those models are null and null and void. Yeah.
Yeah.
When you were designing, a lot of the stuff was battery related in the design, and so what were the other design hardships that were not battery related? What other things did you discover?
Generator controls, getting controls that would work seamlessly between the microgrid controller and the generator. That was a little bit of a challenge. Um, Getting the generator to synchronize with the battery, so that you could get them to operate in parallel, have the right voltage and right frequency. That was a bit of a challenge. Um, God, what else?
Okay, I think.
Yeah,
Oh,
that was a big one.
yeah. All right. Unless somebody has an objection, I think I've covered most of the material that was being asked about. And so we've got Katie back to wrap up. Thank you. Yeah, wonderful
Yeah, thanks,
discussion.
Robert. Thanks for all the questions. And
Sure. Well,
I'm gonna
thank
I'm
the
gonna say,
audience.
I am going to throw this up real quick, our contact information, just so you've got this before you leave. Um, oh, we got this one actually. We got one last question, Scott, from Nicole.
yeah,
And I like this one. It sounds like your maintenance and operations staff are highly skilled in troubleshooting. How are
yes.
you able to keep them engaged?
Oh, good. Lots of free lunches and no, no, just yeah. We keep them engaged by keeping them engaged. Yeah, letting them be part of the whole project. They helped to build it. They feel a sense of ownership. So I think that was in some ways probably the most important, is letting them help build it, and then they feel a strong sense of ownership. And then we as engineers stay really, really engaged on keeping things up to date and helping them with maintenance. It's a collaboration process. It's teamwork. Instead of just dumping the system on them, and then okay, you guys got it. You guys got to make it work, and then they just get frustrated. So it's a constant team effort to keep them, and just yeah, have it be fun. So
I love that. Well, Scott, I hope somebody has, um, through osmosis, gotten all of your knowledge because it seems like, you leaving is going to be leave a little bit of a hole. And thank you for taking your time to share with our audience today everything that, and we've got this on recording in case you joined late. We'll have that up on our website within about a week. Give me about a week. And there's Scott's information there, so you can contact him if you think of other questions. Our information if you need to get in touch with us, or if you've got an energy saving or any kind of energy project, go ahead and give the energy advisors a shout, and we'll see what we can do to help you out. Okay.
yeah, feel free to reach out with any questions, because it's fun stuff to talk about, and I'll be more than happy to talk to anybody offline about this stuff.
And lots of cool stuff coming up in the future, like people were asking about and about. So it's going to get even more interesting.
It is, yes, without a doubt. We've got a good future.
Yeah. Okay. We'll see everybody in about a month. I'll have those other events up to register for today. Today. All right. Thank you, everybody. Thank you, Scott.
Bye,
Thank
Katie.
you.
Thanks, Robert. Thanks, everyone. Bye.
Thank you. Appreciate it.